So in this video we're going to be looking at modeling harmonic motion using sine and cosine functions. So first we'll just kind of quickly explain what harmonic motion is. So harmonic motion is a motion that occurs in a setting where you have an equilibrium point. So you have an object that has a natural resting point, equilibrium, and what you do is you displace that object from equilibrium so that some restorative force tries to return it to its equilibrium position, and it overshoots the equilibrium position and it begins to move back and forth between two extremes, passing through its equilibrium. And as long as we ignore damping forces or forces like energy loss in a system or air resistance, it doesn't return to equilibrium. It just keeps moving back and forth in what we would call simple harmonic motion. So two kind of classic examples of harmonic motion are spring motion and pendulum motion. Pendulum. So in the classic spring motion example, what you do is you hang a spring, and that spring has some mass attached to it. And the mass stretches the spring until it's resting. It's in the spot that's in complete equilibrium. It's not moving up or down. And usually you call that line your equilibrium line. So this is at rest or at equilibrium, and this is going to be 0 units. So let's say we decide to measure in inches. This would be the 0-inch mark. And then what you do with that spring is you displace it. You put it out of its equilibrium position. So let's say we stretch that mass down so that it's 4 inches below its equilibrium point. And for convention's sake, we'll make down negative. So you make this -4, indicating you've stretched it -4 inches below its equilibrium. Well, if you let that mass go, it's going to want to rebound. It's going to want to shoot back up, but it's not going to stop at its equilibrium position. It's going to move through its equilibrium position until it hits 4-inch mark above it. And again, this assumes that we ignore any damping forces. We ignore energy loss in the system. We ignore air resistance. So we get this, that's why we call it simple harmonic motion, because we're ignoring all of those things that would, in our experience, return the mass eventually to its equilibrium position. So the key is that we displace it below equilibrium. It moves up to a height 4 inches above its equilibrium point, and it's going to return back down to where you stretched it initially. And let's say it takes 2 seconds to move through that distance. So this would be the period. The period is how long does it take if you release something from a position? How long does it take for that thing to return back to that same position? So period, I'd say, hey, if it takes the mass 2 seconds to get back to where I initially pulled it down to, then my period is going to be 2 seconds, or 2 seconds per cycle. A cycle means it goes through everything that it can do once and it returns back to where it started. So frequency is always going to be the reciprocal of the period, because frequency just wants cycles per unit time, and period is always going to be the reciprocal of that. So if it takes 2 seconds to do 1 cycle, then it takes 1 cycle to do 2 seconds. So the relationship between period and frequency is they are always reciprocals of each other. And usually you would just put 2 seconds per cycle and 1/2 cycle. Can't even spell cycle today. Cycle per second. And of course amplitude is going to be the max distance that you get from your equilibrium point. So in this case, the amplitude is 4 inches for this example. I never get more than 4 inches above or below my equilibrium point. So this would be spring motion. And then the other example is pendulum motion. So in pendulum motion, you also have a natural resting point or a natural equilibrium point, which is important for harmonic motion. So this equilibrium point would be, hey, I hung a bob or some metal piece at the end of a pendulum arm, and it wants to, because of gravity, just sit in this down position. This is its natural 0. So this might be 0 inches. And then with the pendulum, you can move it from its equilibrium point. You can agitate the system and say, I'm going to move you through some arc, let's say clockwise, through some arc length S. This move you through an arc length of S inches to some maximum height. And then I'm going to let you go. And if you do that, then the pendulum is going to swing back through its equilibrium point, just like the mass over here. If we pulled it down, it comes back through its equilibrium point on its way up and on its way down. Well, here the pendulum would move down through its equilibrium point, and it would overshoot it, and it would wind up back at an arc length here of S inches. So just like with the spring mass system, you have to decide, do you want, if you move something to the left of equilibrium, do you want that to be positive or negative? So let's for our purposes say, hey, we're going to say if we move it this way, that's going to be positive inches, and if it moves to the right of equilibrium, we're going to call that negative inches. So if we do S inches to here, it's going to swing through to negative S inches up on the other side. And once it gets to the high point, it's going to want to swing back through and return to where it began. And if we said, hey, that happens in 1.5 seconds, then that's 1.5 seconds per cycle. And it's also 3 halves is 1.5 seconds. So the frequency, if this is the period, then the frequency would be the reciprocal of that. It would be 2/3 cycles per second. Remember, seconds per cycle is a ratio, and its reciprocal would be cycles per second. So this is another natural example of harmonic motion. And the key is, if we have harmonic motion, we can come up with sinusoidal models for these motions. So here's a concrete example. Harmonic motion. Suppose you have a mass suspended by a spring, and that mass is at rest. You then pull the string 3 centimeters below equilibrium. You release it. I should have said that you release it. It doesn't say that, but you release it. And once you release it, let's say it returns back to the position to which you pulled it 2 seconds after you release it. Oh, there's the word release. So A, draw a sinusoidal graph that models the scenario. So this is a cosine sine type of a graph. Find a cosine or sine function that models it, and find the period and the frequency. So A will be to draw a sinusoidal graph. B will be to come up with the sinusoidal model, and C is to come up with the frequency. In fact, we've already been given the frequency, or sorry, the period. We're told that it takes 2 seconds once you release the mass for it to return to where it began. So we could actually start, hey, the period is going to be 2 seconds. And it starts and returns, so that's 1 cycle. And once we know the period, we know the frequency, because the frequency is the reciprocal of that. It's 1/2 cycle per second. And we left the word per out of there. So if we start with a rough sketch, before we do the sinusoidal model, we know that we have a mass. It is suspended on a spring. It's at equilibrium, which is the 0 mark, and we're measuring in centimeters, so this would be the 0 centimeter mark. If we then pull that mass down 3 centimeters below equilibrium, we'll be at the -3 centimeter mark. When we release it, it will bob back up, ignoring any damping forces, to a 0.3 centimeters above equilibrium, and then it returns back to whence you released it in 2 seconds. 2 seconds to get back to where you released it from. So what we're going to do is take this picture and create a sinusoidal graph for the situation. And so we want to recognize is that we're going to have a displacement axis. How far have we displaced the mass from its equilibrium? And we're going to have a time axis. What is the point at which we are in our displacement process? And if I pull myself down below equilibrium and I start from the -3 centimeter mark, that would mean I'm starting at a point below equilibrium. And as I move upwards, I'm going to have a point in time where I return back to my equilibrium point, and then I will shoot to a maximum value above my equilibrium point. I will then bob back down to my equilibrium point, and I will return back to the original displaced position. And all of this takes, we're told, 2 seconds to happen. So this is the 2-second mark right here. And here I have a sinusoidal model, and I can put in some labels. This is 3 inches above, this is 3 inches below equilibrium. It happens in 2 seconds. We can do all of the nice things we're usually expected to do with graphs. Label our axes, put some tick marks in. This is one period. We know from our work with sine and cosine functions that it's broken into 4 equal parts, and if we want to label those tick marks, we just take with the period number 2 and we multiply it by a 1/4, which will give us a half. So we know these are in 1/2 inch increments, so this would be 1 out of 2, 2 out of 2, 3 out of 2, and this one would be 4 out of 2, which simplifies to the 2 seconds, and of course 2 out of 2 is the 1 second mark. So this is Part A, draw a sinusoidal graph that models the scenario. Part B says, come up with a cosine or sine function that models this graph. So we want to take this graph and derive from it a model. So we know that we have displacement on the output axis, and it's a function of time. We know that the amplitude is 3 centimeters. So our vertical stretch on either a sine or cosine function is going to be 3. And then we need to decide, are we going to use a sine function or cosine function to model it? Well, if I use a cosine function and I'm starting here, usually a cosine function starts up high and comes down low. I would need to reflect a cosine function, but I wouldn't need a horizontal shift. And because the midline is at 0, there is no vertical shift going on. So let's do cosine first. So if I'm using the cosine function, I'm starting down below the midline instead of above, so I would need to reflect the cosine function. There is no horizontal shift needed if I reflect, so I'm just going to have something of the form b times t, and there's going to be no vertical translation going on out here. So I just need to figure out what b is, and if you're in a science book, if you're in a physics text or differential equations course, instead of b, they would use omega here, omega t. We don't need to do that. It's outside the scope of what's important to us. We just want the cosine model. So b times t. We need to figure out what b is, but we know the period is 2, and this is the t-axis. So t equals 2 needs to correspond. This is 1 cycle, needs to correspond to 2 pi radians, or 1 trip around the unit circle. So we take our b times t. But we see that t is 2 for 1 trip to happen, so we need b times 2 to equal 2 pi, or 1 trip around the unit circle, 1 cycle, 1 time around the circle. Divide both sides by 2. We see that b needs to equal pi, so we'll update the model with pi. And again, this would be omega instead of b if we were in a physics textbook. So this is a cosine model for the situation. Let's suppose instead we wanted a sine model for the situation. Well, we know with the sine model that the amplitude 3 and the scalar that we use to adjust the period correctly are the same for both models. So the 3 and the pi we've already solved for. We would just need to identify what needs to be done to the sine function, the toolbox function, to get it into the correct position. What I want to notice here is that if I were to take the sine function, which usually starts at the origin and goes up, I would need to horizontally translate it 1/2 unit to the right. So that's what we would need to do to the sine function. We would need to say, let's kill our axis. I just killed my whole axis. So with the sine function, I would say the amplitude is going to be the same. I don't need to reflect. The sine of pi, and usually we do this pi t plus c thing inside of here, and then we factor the pi off. And then we recognize that this is the horizontal shift going on here. So I tend not to start with it in the bt plus c format. The way I like to think of it is, I know the scalar I need to adjust my period correctly. I know that the horizontal shift has to be applied directly to the input variable, not pi times the input variable. So I'm going to isolate my input variable with the scalar that's here to adjust the period correctly. I'm going to isolate my input variable and say, let's apply our shift directly to the input variable. The shift is 1/2 unit to the right, so I subtract a half to get the horizontal shift of 1/2 unit. And then to put it into standard form, I can distribute this pi into parentheses. 3 sine pi t minus pi over 2. So again, sine and cosine function can both be used to model the scenario. So we'll do one more example with the pendulum. So here it says we have a pendulum bob at rest at the end of a 24-inch pendulum. So I have some pendulum hanging from a connection point. There's a bob at rest. This is the 0 mark, and it's a 24-inch pendulum. That turns out to be extraneous information, but that's okay. So this will be 0 inches at our equilibrium point. And we then move the bob leftwards through an arc of 20 inches. We move the bob leftwards through an arc of 20 inches. And again, we'll take the convention this time that a leftward movement through an arc is going to be positive. So that's going to be positive 20 inches. And we release it, and let's say it takes pi over 2 seconds to return to the position from which we released it. So we release it, it zips down through equilibrium, ignoring air resistance and mechanical energy loss. We move back through an arc. This will be negative 20 inches on this side. We get to our peak, we then return back through equilibrium, back to where we started, and that takes pi over 2 seconds to do. That's our period. So the period is always that length of time it takes to do one cycle. So the period is going to be pi over 2 seconds per cycle, one trip of the pendulum bob. So the frequency is the reciprocal of that, because it's cycles per unit time, so it's going to be 2 over pi cycles per second. And we are supposed to draw a sinusoidal graph that models the scenario. So again, I'm going to have an output axis that describes my displacement as a function of time in inches. I'm going to have a horizontal input axis that represents time measured in seconds, and we'll put all our standard little features on our graph, and we're displacing it from equilibrium. So this 0, the x-axis, or the equation d equals 0, is our equilibrium. We're displacing it by moving it 20 positive inches through an arc. So we're starting up high, and then as we move down from our initial displaced position, we'll pass through equilibrium. We'll wind up displaced 20 inches over here through this arc of 20 inches. We'll move back to our equilibrium as we come back the other direction, and we'll wind up back where we started at our original position, displacement position, and that happens in pi over 2 seconds. So labeling things in, this is 20 inches to the left of equilibrium, 20-inch arc to the right of equilibrium, happening in pi over 2 seconds. We know that one period is always chunked into 4 nice increments. So to take the period number, to get the first tick mark, we would take a quarter of that if we wanted to label those. So we would get pi over 8. So this first tick mark would be at pi over 8. And then it would be 2 pi over 8, 3 pi over 8, 4 pi over 8, which simplifies to pi over 2. So once we get it, we can always just count up, which is a nice way to do it. So there's our sinusoidal graph. We've labeled the axis, we have our arrows, we have one full period of the pendulum bob movement. So it looks like a pretty good graph, and then it's just a matter of finding a model for displacement using sine or cosine function. So cosine function actually is the most natural function to use to model this because I'm starting high and going down. That is how the cosine function likes to work. So displacement as a function of time. The amplitude is 20. Amplitude is that max distance we get from equilibrium, either above or below. So we get a vertical stretch of 20 units on the cosine function. No reflection needed. We don't need a horizontal shift because we're starting in our natural position, and we don't need a vertical shift because the equilibrium is the line d equals 0, so we're on the axis. And this is going to be b times t. Again, science text, especially physics, diff EQ, you would have omega here. We're not going to worry about this. And the key is that the period happens in pi over 2 seconds, so t equals pi over 2 at one cycle or one trip around the unit circle. So we need to plug pi over 2 in for time, so it's going to be b times pi over 2, and we need to know when does that equal 2 pi. We'll multiply both sides by the reciprocal of pi over 2, because when we multiply things by their reciprocals we get 1. 1 times b is b. Pi divided by pi is 1. 2 times 1 times 2 is 4, so b equals 4. And there's a cosine model. If we wanted to model it with the sine function, we could say, hey, look, if I shift over pi over 8 units to the right, I could use a reflected sine function as my model. Again, the 20, the amplitude stays the same. The scalar that adjusts our period stays the same. So I would say, hey, it's going to be 20, but I want to reflect. Here's my sine function. Reflect the sine function, which would usually go up when it starts on the midline. Reflect it. Use the sine function. This number isn't going to be any different for the sine than it is for the cosine. We'll isolate our variable t from that scalar so that we can apply our shift directly to the input variable, and the shift needs to be pi over 8 units to the right, and then we can distribute to get this written in a standard form. We get negative 20 sine 4 times t minus 4 times pi over 8 is just pi over 2, and we have a sine model for a sinusoidal motion.